Picture this: a developer on your team pushes a commit with a subtle type error buried in a utility function. Without CI, that error rides into production, surfaces at 2 in the morning, and costs the team 3 hours of debugging. With the pipeline we're about to build, that error gets caught in under 2 minutes automatically, on every single push and pull request. In this chapter we're building a complete, production-grade Node.js CI pipeline from scratch. Not a toy example, a real workflow with 4 quality gates: ESLint to catch style bugs and bad patterns, TypeScript's type checker to catch type errors before they become runtime explosions, Jest with coverage to catch logic regressions, and finally a real TSC build to verify the compiled artifact actually produces valid output. By the time we're done you'll have a single YAML file that any Node.js TypeScript project can drop in and use immediately. You'll understand not just what each step does, but why it's in the order it's in, because the order matters, and we'll show you exactly how to think about it. This is the pipeline that senior engineers build on day 1 of every new project. Let's build it together. Before we write a single line of YAML, let's understand our weapon of choice. Every tool in this pipeline has a specific, distinct job, and there's no overlap between them. ESLint is your static analysis layer. It reads your source code without executing it and flags things that are almost certainly wrong, and used variables, using double equals instead of triple equals, for getting to await a promise, calling console.log in code that's headed for production. ESLint is like a very experienced code reviewer who reads every file you write. TypeScript's TSC is your type safety layer. It enforces every type annotation you've written. Pass a string where a number is expected? TypeScript catches it. Try to access a property that might be null? TypeScript catches it. An entire category of runtime errors, the ones that would silently corrupt data or throw exceptions in production, get caught at compile time instead. Jest is your logic verification layer. Unit tests exercise your actual business logic with real inputs and expected outputs. If someone refactors a utility function and accidentally changes its behavior, Jest catches the regression. The coverage report tells you what percentage of your code the tests actually exercise. And finally, TSC build is your artifact verification layer. It confirms that the code doesn't just type check, it actually compiles into valid JavaScript output. This catches configuration issues in sconfig, missing path aliases, and output directory problems that are invisible to the pure type check step. 4 tools. 4 different bug classes. Together they form a gate that almost nothing slips through. Here's a mental model that will serve you for your entire engineering career. Think of your CI pipeline as a series of increasingly fine-grained nets. Each net catches a different class of bug, and the bugs that escape one net get caught by the next. ESLint is your coarsest net, it catches the obvious, surface-level problems. And used variables, questionable patterns, style inconsistencies that make code harder to read and maintain. ESLint runs in seconds and gives you immediate feedback. TypeScript is a much finer net. It catches the structural bugs that ESLint can't see: the wrong argument being passed to a function, a missing required field in an object, a nullable value being treated as if it's always defined. These are the bugs that would have caused runtime exceptions in plain JavaScript. TypeScript eliminates whole categories of them at compile time. Jest is your logic net. It runs your actual code against your actual test cases. A function that type checks perfectly and passes ESLint can still produce completely wrong output, a calculation that's off by 1, a sorting algorithm that breaks for empty arrays, an API handler that returns the wrong status code for a specific error case. Jest catches all of that. And the build step? It's your integration net. Everything before it runs in isolation. ESLint reads files, TSC checks types, Jest runs tests. But the actual compilation step wires everything together and verifies the whole thing produces valid output. That's when you discover that your config has an incorrect path alias, or that you referenced a module that isn't in the bundle. Run all 4 nets, catch almost everything. Before we touch the workflow file, let's orient ourselves in the project structure. GitHub Actions CI doesn't care what your project looks like internally, it just runs commands and checks exit codes. But understanding the layout helps you see exactly what each pipeline step is operating on. Our TypeScript project has a standard, conventional structure. The src directory contains all application TypeScript source files. This is where ESLint and TSC focus their attention. The tests directory contains Jest test files named with the .test.ts convention. Jest discovers them automatically based on the pattern configured in jest.config.js. The dist directory is interesting, it's git ignored, so it doesn't exist when the runner first clones the repo. The build step creates it from scratch. That's intentional. We want to verify that the build process can always produce a clean output from source, not that a previously committed artifact still exists. 3 configuration files are critical to how our pipeline runs. That's config.json tells TypeScript where to find source files and where to put output. The .ESLint.json tells ESLint which rules to enforce and which parser to use for TypeScript. The Jest.config.js tells Jest which files to collect coverage from and what coverage threshold to require. And packagelock.json, this file is the secret to why npm CI works. It's a complete snapshot of every dependency at every exact version, including transitive dependencies. When npm CI runs in your CI environment, it reads this file and installs exactly what's recorded. No surprises, no drift, no it worked yesterday mysteries. Let's trace the complete flow of a CI run from trigger to finish before we start writing YAML. Seeing the whole picture first makes each individual step make much more sense in context. It starts with a trigger. A developer pushes commits to main, or opens a pull request targeting main. GitHub detects the event and queues a new workflow run. Within seconds, usually under 30 seconds, often faster, a fresh Ubuntu virtual machine spins up in GitHub's infrastructure. The first step is checkout. The runner doesn't automatically have your code, it gets cloned fresh every run. The action/checkout action handles this. It clones your repository at the exact commit SHA that triggered the run, so you're always testing exactly the code that was pushed, not some other version. Step 2 is environment setup. The action/setup node action installs Node.js 20, configures npm's cache directory to restore from any previous run with the same dependency hash, and adds node and npm to the path. Step 3 is installation. npm CI reads your packagelock.json and installs every dependency at the exact recorded version. On the first run, this downloads everything from the registry, maybe 45 seconds. On subsequent runs, the cache kicks in and this drops to under 10 seconds. Then comes the quality gate sequence, lint, then typecheck, then test, then build. Each step runs the corresponding npm script, checks the exit code, and either proceeds to the next step or fails the entire job. Fast feedback, automatic, every time. Now let's start writing the actual workflow file. We'll build it up piece by piece, starting with the skeleton, the bare minimum that GitHub needs to understand what this workflow is and when to run it. Every GitHub Actions workflow file lives in the .github/workflows directory and has a .yml extension. We'll call ours ci.yml. The first key is name, which appears in the GitHub Actions UI. We'll use simply ci because it's short, clear, and appears as the check name on pull requests. The on key defines our triggers. We want this pipeline to run on two events, any push to the main branch, and any pull request that targets main. Using both covers our bases, pushes to main run the pipeline on merged code, and pull requests run it on proposed changes before they merge. Together they ensure that main is always in a known good state and that PRs can only merge if the checks pass. The jobs key is where the actual work lives. We define a single job called CI lowercase, short, clear. Jobs run in parallel by default when you have multiple, but we only need one here. The runs on key tells GitHub which type of runner to use. Ubuntu latest is the right choice for Node.js projects. It's the fastest runner, it's free for public repos and has generous minutes for private repos, and it comes with Node.js, npm, git, curl, and most common build tools pre-installed. This skeleton, name, on, jobs, runs on, is the foundation. Every step we add from this point forward goes inside the steps array of our CI job. The first two steps of almost every Node.js workflow are identical, and for good reason. They're the foundation that everything else depends on. Step 1 is checkout, using the action/checkout action at version 4. When your workflow starts running, the runner is a fresh virtual machine with nothing on it except the operating system and pre-installed tools. Your code doesn't exist there. Action/checkout clones your repository, checks out the exact commit that triggered the run, and leaves you in the repository root directory. From this point on, all your files are available. Step 2 is setup node, using action/setup node at version 4. This action does three things. First, it installs the version of Node.js you specify. We specify version 20, which is the current LTS. Second, it configures your path so that node and npm commands work. Third, and this is the critical part, when you set cache to npm, it automatically manages the npm cache directory. Here's how the npm cache works in practice. The action reads your packagelock.json and generates a hash of its contents. It then checks whether a cache entry for that hash exists from a previous run. If it does, it restores the cached npm module directory to the runner. This means the packages are already downloaded and npm CI can skip the network entirely. If no cache entry exists, it proceeds normally, and at the end of the job saves the npm directory as a new cache entry for future runs. On a project with 100 dependencies, this cache optimization takes your install step from 45 seconds down to 8 seconds. A 5x speedup, for free, with 2 lines of YAML. This might be the single most important thing I'll tell you in this entire chapter. In CI environments, always use npm CI. Never use npm install. The difference is not subtle, it fundamentally changes how reliable your pipeline is. npm install is designed for local development. When you run it, npm resolves the semver ranges in your package.json, things like 1.2.3, which means any compatible version. If a new patch version of a dependency was released since you last ran install, you might get it. Or you might not, depending on your cache state. npm install also updates your package.lock.json if it's out of sync with package.json. The install command is adaptive, which is exactly what you want when developing locally. npm CI is designed for continuous integration. The CI in the name literally stands for clean install. When you run it, it first deletes the entire node_modules directory if it exists, guaranteeing a clean slate. Then it reads package.lock.json, not package.json, and installs every dependency at the exact version recorded in the lock file. It doesn't resolve ranges, it doesn't consult npm's registry for newer compatible versions, it installs exactly what the lock file says. Here's the behavior that makes it truly trustworthy. If your package.lock.json is out of sync with package.json, meaning a developer added a dependency to package.json but forgot to commit the updated lock file, npm CI exits with a non-zero status code and fails the job immediately. This catches the classic works on my machine scenario, where a developer has a dependency locally that hasn't been properly recorded for everyone else. npm CI is deterministic. It produces the same result every time, on every machine, in every CI run. That's exactly what you need for a trustworthy pipeline. With dependencies installed, we're ready for the first quality gate, lint. The step is simple, a single run command calling the npm run lint script. What makes it powerful is what happens when ESLint finds a problem. ESLint exits with status code 0 when it finds no errors or only warnings, depending on configuration. It exits with status code 1 when it finds actual lint errors. GitHub Actions treats any non-zero exit code as a step failure, which fails the entire job. So the moment ESLint finds a real error, the pipeline stops, no further steps run, and the commit is marked as failing. The developer sees exactly which rule was violated and on which line. The reason lint runs first in our pipeline is pure economics. Lint is typically the fastest check, 3 to 8 seconds for most projects. If there's a lint error, we want to know immediately, without waiting 30 seconds for tests to run or 20 seconds for type checking. By ordering from fastest to slowest, we minimize how long developers wait for feedback on broken code. The ESLint configuration for TypeScript projects needs the TypeScript ESLint parser and plugin. The parser understands TypeScript syntax that standard ESLint can't parse. The plugin provides TypeScript-aware rules, things like flagging and used variables in a way that correctly handles TypeScript's type-only imports. The recommended rule set for TypeScript ESLint is a great starting point for new projects. One tip worth adopting for greenfield projects: add max warnings 0 to your lint command. This makes ESLint fail on warnings too, not just errors. Warnings have a habit of accumulating quietly until there are hundreds of them, at which point no one wants to fix them. Zero tolerance from day one keeps the codebase clean. Lint passed, now we move to the type checking step. The command is npm run typecheck, which maps to tsc noemit in our package.json scripts. Let's understand that noemit flag because it's crucial. When you run tsc without any flags, it does two things: it typechecks your code, and it compiles TypeScript to JavaScript, writing output files to the dist directory. In the typecheck step, we only want the first behavior, pure type validation with no file output. The noemit flag tells tsc to do the typechecking work completely but throw away any output it would have generated. This keeps the typecheck step fast and prevents it from creating partial dist artifacts that might interfere with the real build step that comes later. TypeScript typechecking typically takes 10 to 20 seconds on a medium-sized project. When it fails, it prints the exact file, line number, and column of every type error. A developer gets precise, actionable feedback in their CI log. After typechecking passes, we run tests with Jest coverage. Jest discovers all files matching the star.test.ts pattern, runs them, and then generates a coverage report that shows what percentage of your source code was executed during the tests. The coverage report appears in the CI log as a text table. You see each file, its statement coverage, branch coverage, function coverage, and line coverage. The coverage threshold in jest.config.js is important. Setting a minimum threshold, say 80% of lines, means the test step fails if coverage drops below that level. This prevents the slow erosion of test coverage that happens when new features get added without corresponding tests. It's a quality gate within a quality gate. All quality gates passed. Now the final step, actually building the artifact. npm run build maps to tsc build, which is subtly different from tsc no emit. tsc build reads your config.json and does a full incremental compilation, writing JavaScript output to the dist directory you configured as outdir. In CI, there's no previous build to be incremental from, so it compiles everything fresh. The compilation verifies that not only do the types check out, but the code can actually be transformed into valid JavaScript files that Node.js can execute. This step catches things that pure type checking misses. A misconfigured outdir ins-config, a missing path alias that TSC can resolve but Webpack or Bundler can't, a module that imports from a path that doesn't exist in the output tree. These are configuration level bugs that only surface when you do the real build. Once your pipeline is working, add a status badge to your README. The badge URL follows a predictable pattern: the GitHub Actions domain, your repo path, the workflows path, your workflow file name, and badge.svg. Drop this into a markdown image link in your README and it becomes a live indicator: green when the last main branch run passed, red when it failed, yellow when it's in progress. Every contributor, every potential hiring manager who browses your open source project, sees immediately whether this project has working CI. Your complete pipeline is now fully assembled. 8 steps, about 80 to 90 seconds end to end, covering 4 distinct quality dimensions. This is the gold standard CI setup for Node.js TypeScript projects. We've built the pipeline. Now let's optimize it. The single highest leverage optimization you can make to any CI pipeline costs 0 compute and 0 money. It's purely about the order in which you run your steps. The principle is simple: always run the fastest checks first. If lint takes 5 seconds and end-to-end tests take 5 minutes, and both of them would fail on a broken commit, you want to find out from lint in 5 seconds, not wait 5 minutes for E2E tests to tell you the same thing while burning compute resources and making the developer stare at their screen. In our pipeline, the natural ordering is already fastest to slowest. Lint runs in about 5 seconds. Type checking runs in about 10 seconds. Unit tests with coverage run in about 30 seconds. The build step runs in about 15 seconds. End-to-end tests, if you have them, should live in a separate job or a separate workflow entirely, because they can take minutes. This ordering isn't just about speed, it's about signal quality. A lint error is the cheapest kind of bug to fix, and the lint error message is extremely clear: wrong file, wrong line, wrong rule. Showing the developer that error in 5 seconds is a much better experience than making them wait a minute and a half for the exact same negative result. When you're building pipelines for larger projects, this principle scales dramatically. A monorepo CI pipeline that runs in sequential order might take 20 minutes. The same pipeline with jobs parallelized and steps ordered fastest first might run in 3 minutes. The code changes are minimal, the architectural thinking is what matters. Jest generates a coverage directory full of rich, human-readable reports. By default in CI, those files disappear the moment the job finishes, the VM is wiped clean. The actions/upload artifact action solves this by preserving files from the runner as downloadable artifacts attached to the workflow run. The configuration is straightforward. After the test step, add an upload artifact step that targets the coverage directory. Give it a clear name like coverage report. Set retention days to how long you want GitHub to keep it. 30 days is a sensible default. The if, always, condition is worth understanding. By default, GitHub Actions skips subsequent steps when a previous step fails. But you want your coverage report even when tests fail. In fact, you especially want it when tests fail, because you want to see which tests ran, what coverage they achieved, and what the failure output looked like. The always function tells GitHub to run this step regardless of whether previous steps succeeded or failed. Once uploaded, the artifact appears in the workflow run summary in the GitHub UI. Anyone on the team can click and download a zip of the coverage directory, unzip it, and open the index.html in their browser to see a beautiful interactive coverage report, every file, every line, with color-coded indicators for covered and uncovered code. For teams that use external coverage tracking tools like CodeCov or SonarQube, the lcov.info file inside the coverage directory is what you feed to those services. They parse it, track coverage over time, and can comment directly on pull requests with coverage diff information. But even without external tooling, simply uploading the artifact as part of your workflow gives you a permanent record of every CI run's coverage state. Here's a scenario that plays out dozens of times a day on active teams. A developer opens a pull request, waits for CI to start, notices a typo, pushes another commit, notices another issue, pushes again. Now there are 3 CI runs queued or in progress for the same branch, but only the last one matters. The first 2 are already obsolete. Without concurrency control, all 3 runs will complete, burning compute minutes and cluttering the UI with old results. With the concurrency key, GitHub automatically cancels the older runs the moment a newer one starts for the same branch. The concurrency group key is the critical piece. It's a string that uniquely identifies a group of runs that should be mutually exclusive. We build it from two context values, github.workflow, which is the workflow name, and github.ref, which is the full branch reference like ref/head/featureauth. Every push to the featureauth branch generates the same group string, so GitHub knows they're competing runs. When run 3 starts, GitHub cancels run 1 and run 2 automatically. The cancel in progress true flag is what enables the cancellation behavior. If you set it to false, GitHub would instead queue the new run and wait for the current one to finish, useful for serializing deployments, but not what we want for CI checks. One important caveat: never use cancel in progress true in deployment workflows. A deployment that gets cancelled mid-flight can leave your infrastructure in a partially updated state, which is far worse than a slightly stale CI run. Use this pattern only for test and build pipelines where a cancellation leaves no persistent state behind. Before we wrap up, let's test your understanding with a question that comes up in real engineering interviews and code reviews all the time. The question is, why should you use npm CI instead of npm install in a CI pipeline? If you've been following along, you know the answer is option C. npm CI deletes node_modules and installs exactly from the log file, making the installation deterministic and failing the job if the log file is out of sync with package.json. Option A is wrong. npm CI does use the npm cache when available, but that's not the primary reason to use it. The speed improvement from caching works with both commands. Option B is the exact opposite of what npm CI does. npm install might update package.json when you use flags like save, but npm CI never updates anything, it's read-only with respect to your project files. Option D is also wrong. npm CI installs all dependencies, including dev dependencies. If you want to skip dev dependencies, you'd use npm install omit equals dev, but you don't want that in CI because your test runner, TypeScript compiler, and ESLint are all dev dependencies. The real answer is determinism. In software engineering, determinism means the same inputs always produce the same outputs. npm CI makes dependency installation deterministic, the same log file always produces the same node_modules. That's the foundation of trustworthy CI. In this chapter you've built a complete, production-ready Node.js CI pipeline. Lint, typecheck, test, build ordered from fastest to slowest, with npm caching, coverage artifacts, and concurrency control. This is the pipeline that protects your main branch. In the next chapter, we'll extend it to run across multiple Node.js versions simultaneously using matrix builds.